Alcohols. Alcohols are classified as either primary, secondary or tertiary. Primary alcohols. So how do you decide if something is a primary alcohol? Well, the carbon with the OH, the COH bit, that carbon there is bonded to one other carbon. Primary means one. So it's got one other carbon attached. By default, therefore, if it's got one other carbon attached, it needs 4 bonds. It's got one carbon attached, an OH attached, and it's got 2 H's. So draw me 3 different primary alcohols. So it could be ethanol, methanol, propan-1-ol, butan-1-ol. The carbon with the OH is at the end of the chain. So it's at carbon number 1, the ol part. A secondary alcohol has 2 carbons bonded to the C with the OH. In other words, the OH is bonded not at the end but somewhere in the middle of a chain. Something like propan-2-ol, butan-2-ol, pentan-2-ol, or even pentan-3-ol. Tertiary alcohols have 3 carbons bonded to the COH. It says here draw and name 3 different alcohols, but you can just do 1 or 2 if you want. That carbon has got 3 different carbons attached, bonded to it. So the COH, that C has 3 different carbons bonded. So if you imagine the COH is in the middle of a chain, somewhere in the middle, and there's another carbon attached. So there's something like a methyl group bonded onto the carbon where the OH is. So something like propan-2-ol with a methyl group also at number 2, 2-methyl propan-2-ol, or 2-methyl butan-2-ol, or 3-methyl pentan-3-ol. So the methyl group, the CH3, is bonded onto the carbon with the OH. That means that that carbon then has 3 different carbons bonded to it. That makes it a tertiary alcohol. How do you test between them? Well, it's difficult to test between primary and secondary alcohols because they are oxidized. That means they've had oxygen added or hydrogen removed, and they turn acidified potassium dichromate from orange to green. So if acidified potassium dichromate goes from orange to green, you know it's a primary or a secondary alcohol. You can't tell which one it is because acidified potassium dichromate will go from orange to green. And what happens is when the acidified potassium dichromate oxidizes the COH, oxidation is adding oxygen, but it's also removing hydrogen. Oxidation, adding oxygen or removing hydrogen. So have a look at this COH. It's become C double bond O. So you take the C double bond OH and you make it into C double bond O. Acidified potassium dichromate turns from orange to green when it does that, and we show the addition of oxygen or the removal of hydrogen by using an O with a square brackets round it. The reaction involving acidified potassium dichromate in the equation is too difficult to write, so we can simplify the use of acidified potassium dichromate with a square bracket O. So we replace acidified potassium dichromate, which has got a complicated equation formula, with O in square brackets. That means somehow or another acidified potassium dichromate is adding O's onto this chemical. So we have ethanol here with an O added. It will make water, and this CH2OH will turn into a C double bond O. So if you have a CH3 C double bond O, you have ethanal. So you've got water and ethanal. So the CH3OH turns into a C double bond O, releases these hydrogens here, and they will react with the O to make water ethanal. You might need to work out how many O's you need, and you might need to put a number in front of those O's there to balance it. Now it doesn't react, it doesn't stop there, the reaction carries on. This potassium dichromate can oxidize ethanal aldehydes into carboxylic acids. So it makes ethanal, an aldehyde from a primary alcohol, ethanal, and the ethanal here that you can write in here with the O will make ethanoic acid, CH3COOH, and balance that as well. One question, an A-level question, is how can you make the ethanal and not the ethanoic acid? And it's simpler than you think, really. All you've got to do is remove the ethanal before it makes ethanoic acid. So what you do is you distill it. As it's being made, you carry out distillation and you distill this ethanal off from the water that's made and any ethanol that's remaining in the mixture. You distill this off before it gets a chance to react again. Let's have a look at a secondary alcohol here. So here, a secondary alcohol. I've done that wrong, so I'm going to make my secondary alcohol here. That is propan-2-ol. So the OH is bonded to a carbon, and this carbon with the OH at carbon number 2, propan-2-ol, this carbon is bonded to two other carbons. In other words, that OH is in the middle of a chain. That makes it a secondary alcohol because the carbon with the OH is bonded to two other carbons. When I react it with O from acidified potassium dichromate, this OH will turn into a C double bond O. So you'll get CH3, C double bond O, CH3. You will make propanone and water. See if you can balance it. Tertiary alcohols cannot be oxidized. A practical theory. So we're due to do a reflux. We're not going to manage to do it at the moment, but what a reflux is, it's anywhere where you need to heat something in a flask, but then you don't want to lose any of the gases. So you put a condenser here upwards, so instead of distillation you put it upwards going here. That means that the liquids here, if they evaporate, will go up into the condenser and any gases will cool and drop back down into the flask. It's a way of reacting this mixture for a long period of time without losing any of the mixture of gases. Some people say you could just put a bung on it and seal it, but the bung would pop off because when you heat up a mixture it expands, and the expanding mixture then would increase the pressure and would blow the cork or the bung off the flask. So it needs to be open to the air so that we can relieve some of the pressure, but we don't want to lose any of this mixture by evaporating it into the air because it would dry out. We want to keep this and carry on reacting it, and that's what the condenser is for. So reflux is when a mixture of liquids is heating to a boiling point for a long period of time to get it to react. You're basically cooking it for a long period of time. Think about a pan of soup on the stove. If you didn't stop it evaporating by putting a lid on it, then it would dry out. Oxidizing a primary alcohol into an aldehyde and then into a carboxylic acid, that's an example of a reflux reaction. So a primary alcohol with acidified potassium dichromate turns into an aldehyde and a carboxylic acid. But it takes a long time to do it, so that's why you have to heat it up for a long time. So turn a primary alcohol with potassium dichromate, acidified potassium dichromate, into an aldehyde and then into a carboxylic acid, you'd use reflux. You need to practice drawing this, by the way. Look, there are no holes anywhere apart from the hole at the top where the pressure can come out. I've got a seal here, I've got water in at the bottom and water in at the top. You could replace this with a pear-shaped flask instead of a round bottom flask if you wanted to. That's quite common if you're heating something up for a long period of time, because a pear-shaped flask is stronger than a round bottom flask, but either would do. So the flask has a condenser vertically above it without gaps between the flask and the condenser. Look, it's completely sealed here. You need to be careful when you're drawing it. Gases are formed which escape from the liquid mixture and cool back into the liquid by the cold condenser and return drop back into the liquid mixture so they can carry on reacting. Any liquids which initially evaporate can then be oxidized back in the flask. In other words, carry on reacting and oxidizing from a primary alcohol into an aldehyde and then into a carboxylic acid. Anti-bump, small pieces of porcelain from broken evaporating dishes are added to stop big bubbles forming in the flask.